Okay, so let's learn about the rate law, which is also called the rate expression or the rate equation. They mean the very same thing, so don't get confused when you see those different terminologies. So why is there a rate law? That is the thing that is the question that we should ask. Well, why does this exist? It exists because when you change the concentration of one of your reactants, it usually often changes the rate of the reaction. So that's pretty important. So what the rate law allows you to do is it allows you to understand how changing the concentration of either reactant or both reactants will change the rate of your reaction. So it's very useful in the sense of understanding the kinetics of a chemical reaction. So let me give you an example of what I'm talking about here. Let's say that you have one reactant. Let's just say reactant A reacts with itself. So 2 moles of reactant A are going to form product B. So what the rate equation does is it tells you that the rate is equal to some sort of proportionality constant, I'll get more to that in a second, times the concentration of A. Now, don't let this confuse you or intimidate you. It's not going to be an exact relationship without some sort of proportionality constant. So if you double the rate, it's not always going to double this, or if you triple this, it won't triple that, because of a proportionality constant. Otherwise, every single reaction that we know of would just be, it just depends on what you do to A is going to affect what you do to the rate. So what this does is for a specific reaction, this is always different. It's only good for a specific reaction. In this case, 2 moles of A react to form a mole of B at a specific temperature. So you can only use K for a certain reaction at a certain temperature, and then you can definitely plug in the concentration of your reactant, multiply it by the proportionality constant, and it will give you the rate. So this will be different for every type of reaction and even the same reaction at different temperatures. So now that we understand that this is just going to be a component of our rate equation, depending on what reaction we're doing and what temperature we're at, I'm just going to get rid of this for a second because it's really a constant for changing the concentrations, and it's going to apply to every trial of every experiment that we do to find information we need to find about changing this concentration of A and how it's going to affect the rate. So let's just say the rate constant is 1. So then I will just get rid of that and just say rate equals concentration of A. So if you remember the definition for the rate law, or why we have a rate law, it's because oftentimes changing this concentration will change the rate of the reaction. But I said oftentimes, I didn't say every time. Let me give you an example. Let's say that we double the rate here. So the rate equals, and let's say our concentration of A is 1. We'll just use easy numbers, and that helps in these types of rate law problems if you have to figure out what happens if you double or triple something. It's always nice if you just start out with a concentration of 1. So if the concentration of A is 1, that means that when, in this situation, the rate equals 1. But what happens if we double the concentration of A? Well, then we're going to go rate equals, well, then rate equals 2. So if we double the concentration of A and it doubles the rate of the reaction, which is what we did here, we just simply said, well, doubling it will make it a 2. This is called a first order reaction because the exponent that's not written, the convention is if it's a 1, you just assume it's a 1, just like the coefficient here in front of B. We don't write a 1 in front of B because we just assume that there's 1 if there's nothing written. Well, the same thing here with these brackets. By the way, these brackets mean the concentration of A. So this is called a first order. First order, we would say first order with respect to reactant A. So you do experiments, you change the concentration, you see the change in rate. We'll talk more about that a little later. And then you'll find out that when you do all the math and you plug in all of the information, you can find what order your reactant is. So what would a 0 order reactant look like? Well, let's just start this whole process over, and let's see. Sometimes we do our experiment and we realize that this is a 0 order reactant, 0 order with respect to reactant A. So we would make this a 0. So watch how this is going to affect all. Let me erase all of our trials here. Watch how this is going to affect the rate. If a reactant is a 0 order reactant, watch what happens. So what happens when I double the concentration of A? Well, let's do our simple math here. Let's say the concentration of A in this trial is 1. 1 to the 0 power is 1. So there's the rate. Now over here we're going to double the concentration of A. Well, let's put that to the 0 power. Well, 2 to the 0 power is 1. Notice that changing the concentration of A, doubling it, I could have put a 3, I could have tripled it. Any way I change the concentration of A, double, triple, quadruple it, it's not going to have an effect on the rate. And that's where we have a 0 order with respect to reactant A. I'm going to tell you how you find this order in a little bit, but I'm just trying to show you how the whole rate law is designed to help us understand how when we change the concentration of a reactant, how is that going to affect the rate? And it's simply realizing that rate equals a proportionality constant, don't let that intimidate you, times the concentration of a reactant to some order, times if there's any other reactants, the concentration of those reactants is some order. Let's do the last example, and then we'll go into some other multi-reactant reactions, and we'll see what happens. So I'm going to get rid of this, I'm going to get rid of this, I'm going to get rid of this, and I'm going to get rid of this, and let's put second order. So if something's second order, let's say reactant A, it's second order. So what that means is we just put a 2 here. That's second order. So it's either going to be 0, 0 order, first order, or second order. So if it's second order, we can run through this little test again, and we can say that 1 squared is 1, 2 squared is 4. So notice that we've quadrupled the rate when we double the concentration. Remember, concentration is in these brackets, and I've just set up 2 trials, so to speak, where I do an experiment with this concentration of 1 and I get a rate. I do an experiment with this concentration and I get a rate. So let's summarize the 3 different scenarios that you would see. If a reactant is 0 order, it has no effect on rate. If it's first order, it has I'm going to call it a 1-for-1 or a linear effect. Meaning that if I double the concentration, I double the rate. If I quadruple the concentration, I quadruple the rate. And then there's a second order. And if a reactant is second order, that means it's an exponential relationship. So let's do another column here. So doubling concentration. Let's see what happens there. And then I think you'll understand these different facets here. Okay, so we made a little table here. Go all the way over here. So this is the order. It can be 0 first or second order. I'll put reactant order just to remind you that we're only talking about reactants. We're never going to say the order with respect to a product. We're just going to talk about order with respect to a reactant. Effect, and then we'll say doubling the concentration of reactant. Of reactant. And if it's a 0 order, there's no effect on rate. If it's first order, we double the reactant. If we double it, then it will be double the rate, or twice as fast. Second order, if we double the concentration, oops, sorry about that, it'll quadruple the rate of reaction. So the question you might have now is, well, how do we find out what the rate, the order with respect to a reactant is? Well, you have to do that experimentally. And let's go ahead and do a quick experiment. We'll have 3 trials: trial 1, trial 2, trial 3. And let's say that our reaction is going to be 3 moles of A react with a mole of B to produce 1 mole of C and a mole of D. You don't have to worry about coefficients when we're doing these kinetics rate law problems either. So what are the factors? Well, we have 2 reactants. We have the concentration of A that we've got to contend with. We have the concentration of B that we need to think about. And then, oops, and then we have the rate. Okay. So what is the possible rate equation here? Well, rate equals a proportionality constant specific to this reaction here at a certain temperature times the concentration of A raised to some power, we'll say X, times the concentration of B raised to some power, we'll call Y. And we know X would be the order with respect to A, Y would be the order with respect to B, and it's only going to either be a 0 here, or a 1, or a 2. So we do an experiment, and in trial 1, we're going to say, let's just set this as 0.1 moles per cubic decimeter, and here we'll say 0.10 moles per cubic decimeter, and let's just say our rate per hour is 0.50. We have to do another experiment, and we're going to hold one of these reactants constant. So we'll hold B constant. We don't have to double, we could even triple the concentration of A. It's okay, you don't have to have an exact amount, whether you're doubling, tripling, quadrupling. And then we see what the resulting rate is, and here's the rate. So now we can immediately realize that A is not going to be a 0 order reactant, because since we held B constant, the only thing that we changed was A, and we saw that it did affect the rate. So it's either going to be a first or second order reactant. How do we find out? How do we do this? Well, why do we hold B constant? So when we do this problem, we can say B is a constant, so we don't need to be concerned about it. Because we're holding it constant, it's not changing. So the overall change in it is it's not changing. 0.1 over 0.1 is 1, and anything times 1 is itself. So we can get rid of B. We can also do the same for K because it's a constant. It applies to every one of these trials and every because we're doing these all at the same temperature. So for the purposes of determining the rate or the order with respect to A, all we need to do is compare two trials. And we do that by taking a ratio of one trial, and let's do trial 2 compared to trial 1. This is enough data to find out the order with respect to A. So we'll say the rate of trial 2 is 4.50. The rate of trial 1 is 0.50. And that's going to be, this is going to be to some power here, the concentration in trial 2, which is 0.30, divided by the concentration in trial 1, which is 0.10. So we're going to get 9 equals 3 to some power. And I think you can clearly see that x equals 2. 3 squared is 9. So this reaction is second order with respect to A. So I can erase that little x there, and I'm going to put a 2. I'm going to erase all this other stuff so we can find out the order with respect to B. So now what are we going to do? We're going to hold A constant, and we're going to test our change to reactant B. So let's do that. 0.30, we're going to hold A constant, and now let's just double reactant B, and we'll see that, oh, well, when we doubled reactant B concentration, it had no effect on the rate of the reaction. So we immediately can state that B is going to be 0 order We can just pick that up looking at the data. But suppose for a moment we didn't know that and we just really wanted to make sure. Well, how do we do that? It would go like this. We would understand that we're holding A constant. We don't know B. We don't know what B is. Let's just put a Y there. We don't know the order with B, I should say, with respect to B. And if we hold A constant in trials 2 and 3, we can just go ahead and say that's held constant. We don't need to worry about the K rate constant either. So now we can simply go ahead and do the same thing we did for the other reactant. And we'll say, well, the rate in trial 3 over the rate in trial 2. And then we'll say the concentration of B in trial 3, which was 0.20, over the concentration of B in trial 2, which was 0.10, raised to some power, Y. We get 1 for this, and we get 2 for this. So can we see that the only thing that works out for Y is Y must equal 0? So we can write the rate equation. The rate equation for this reaction is rate equals, we put in the little k. I'll show you how to solve that in the next video, how to find k based on this experimental data. We write the reactant A in brackets, meaning, and this is a second order reactant. I'm not even going to include B in the rate equation. And the reason why is because it's 0 order. It doesn't make any sense to include it in the rate equation because it does nothing to affect the rate. So this is your rate law, rate expression, rate equation for this reaction. 3 moles of A plus a mole of B yields a mole of C product and a mole of D product. I hope this video was helpful, and I hope you have a great day. Thanks.